Welcome to Math 105, Chapter 7.5, Conditional Probability and Independence. So conditional probability suggests that we find the probability of a given event that another event has also occurred. Hence, there is now some sort of condition that needs to be met. So how many times have you seen an ad on TV, Facebook, TikTok, whatever social media platform, or on a billboard, you name it, and you decide that you like the ad enough to just investigate, right? So you've seen something and then you investigate. Now, whether or not you purchase it is up for discussion, but ultimately there's some sort of catalyst that happened for you to go looking into purchasing a product or whatever we're talking about, right? So for instance, right, we had the Super Bowl not too long ago. And so some of us are strictly watching it for the game, others are watching it for the funny commercials. And can you think of any sort of memorable commercials that you can recall if you did watch it? Well, this year there was one with Aubrey Plaza. She was doing a Mountain Dew commercial, or the Beckham's doing an Uber Eats commercial, right? Those are a few that were standing out to me, right? And I thought they were so funny that I now included them in my notes, right? So then it says we could be asked to find the probability of purchasing the items given that we saw the commercial being what prompted us to buy the product. As you're going to go through these various problems, I want you to ask yourself, what's the reason behind the output? So now conditional probability has an equation. This equation says the probability of A such that, or given that, B has occurred. So again, I'm going to reread that. So A has not happened yet. So A has yet to occur. However, B has already occurred. Right? And this little line we saw back in, I want to say 6.1, is called given that, or such that, or if. Anything that suggests something that has followed has already happened. So if that's how we read it, then we have the equation, the probability of A and B happening over the probability of B, right? Since B has already occurred, we have its probability, and we're waiting for A to occur. So then we're finding that these are happening together, right? A and B result. Now we have to keep in mind, because B is in the denominator here, the probability of B is not equal to 0 ever. So it's not able to have an impossible event. Now to look at it, right, the probability of B is this whole circle, right? So if we're looking at the probability of A, given that B has happened, we're looking at the probability of A and B, so this section right here on top, right, divided by this whole thing in order so that B happens and then A occurs. So the best way, so bear with me. If this isn't making sense quite yet, just bear with me until we get to a couple of our problems, okay? So it says, note in the expression P, the probability of A such that B, A is an event who we want to know, given that you already know B has occurred. So by asking what the condition is, you can also figure out what has already happened. So again, I would say, what did I say in class the other day? Kind of bear with me until perhaps example 2, okay? So kind of a quick example. It says, if there is a 50% chance of rain, R, and a 10% chance of it's both raining and lightning, then the probability of lightning, given that it's raining, is. So then what is the condition? What is the catalyst, right? What is happening right now? So the probability of lightning, given that it is raining, so it is raining right now. You can't have rain without lightning, right? That is totally possible. You can also have lightning without it being raining, right? So they're not mutually exclusive, right? However, right now we know it is raining. Rain is happening. So we know the probability of rain is equal to 50% or 0.5. So if we're looking at your probability, right? We're looking at the probability of lightning, given that right now it is already raining, right? It's already raining. And we want to know, well, what's the probability that lightning will also then result? So it's now the probability of lightning and rain happening together divided by the rain. Now we said the bottom is 50% or 0.5, which means the top, well, we said, well, 50% that it's raining, and then 10% chance of both rain and lightning. So we're going to include that on the top here. Putting that into your calculator is 20%. Now this 20% means what? It means if it is raining, there is a 20% chance that lightning will then result. So it's under the condition that it's raining to start and then lightning will occur later. Again, try to bear with me a little bit. We're just kind of understanding the flow of this equation. And then when we're talking about your decision tree, then it should kind of click into place. So example 1, it says, if you roll a fair dice twice and observe the numbers facing up, find the probability that the sum of the number is 8, given that the first number is 3. So pause the video, see what you can come up with. Now, what is the condition or what has already happened? Well, we're looking for the probability that the numbers add to 8, given that the first number is 3. So your first number is 3 has happened. First number rolled is a 3. So first numbers rolled is a 3. So what would that look like as far as a set? Well, we can have 3 and 1, 3 and 2, 3 and 3, 3 and 4, 3 and 5, and 3 and 6, right? So because they didn't give us much context to this problem other than, hey, we want to find this probability, we're going to have to do a little bit of work, right? So the first number rolled as a 3 has how many options? We'll label this as the probability, or this can be the set first number is 3. So the probability that you roll a 3 first is what? Well, we have 6, 1, 2, 3, 4, 5, 6 ways to have a 3 first out of how many? Well, we got 36 different ways of it when it's all possible. Again, we don't care so much if it's distinguishable or indistinguishable, right? Because it's going to come up no matter what. We're looking at the sum. So we're just going to be using 36. So this is 1 out of 6. ways. So then now let's calculate if that's the number of ways the first number can be rolled is a 3. Now then we have to figure out, well, what is the probability? So we want to know that the first number is 3 and they sum to 8. So what does that look like? Right, well, they sum to 8 is a 3 and a 5, right? And so this is one way. If there is another way, right, 5 and a 3 still does come up with an 8, but notice that the first number that's rolled needs to be a 3. So this does not get included. So the probability that the first number is 3 and the sum to 8 is 1 out of 36. All right, so now let's put it all together. We're looking for the probability that the probability that it sums to 8, given that your first number is a 3, which equals the probability that they are both happening, a 3 and, we'll just do 3 and an 8 over the probability of a 3, which we said is 1 out of 36 over 1 out of 6. We can put that into your calculator. We could also do a little bit of algebra. If you have a fraction over a fraction, then you can keep, change, flip. You flip your other fraction upside down, and then it's just, again, 1 out of 6 or 17%. About 17%. Okay. All right, so I'm hoping that you guys are getting the hang of it. This one was a little bit more involved because it didn't give us your percentages. So instead, we have to figure that out. You could also have done it so that you're looking at one coin. So this is just one coin here, and then you toss it again. So then if this is what you're looking at, then you only have 6 rolls to start, and then 1 out of 6, that sort of idea. All right, let's look at the multiplication principle. So we're normally given your formula, A such that B is equal to the probability of A and B over the probability of B, right? Now let's say, though, we have everything except for this value here. This is what we need. So we need to do a little bit of algebra and multiply the probability of B to the other side. This will cancel with this one, so that if we have any sort of condition that needs to be met and we don't have the and portion of it, then we can certainly build your equation. The probability of A and B is equal to the probability of B, the probability that something has already happened, times the probability of A such that B, or A given that B has happened. So this would be your equation if there's any sort of given condition and we're trying to find that overlapping amount. So for example, right, a quick example. If there's a 50% chance of rain R and a 20% chance of lightning, if it rains, then the probability of both lightning and rain is what? So we said the probability that it's raining is 50% or 0.5. The probability, the chance of lightning, if it rains, so if it rains is happening, the chance of lightning following is 20%. So lightning, given that it's already raining, is 20% or 0.2. And we want to know, well, what's the probability that it's raining and lightning together. We said in this case, we're just going to multiply the probability that it's raining times the probability that it's lightning, given that it's already raining. So there's rain and then some lightning occurs as that results. So 0.5 times 0.2 is equal to 0.10. Now we can compare this to what the first example was, and we do see that those are the same just by switching around your equals, your equation. So now let's try to see this in a decision tree. So we have been doing a lot of practice with this decision tree aspect. So now we're actually going to figure out, well, what does the decision tree, what have we been doing, actually mean in the big scheme of things? Now, in your textbook, it has already given us some of these values. And I'm going to just kind of skip over what your book does. However, it is a really good example. We just don't have enough time to go through it. So I would suggest reading your book as to how they got some of this answer from start to finish. So it says A is going to be a purchase product, and B is going to be that you saw the ad, right? So you saw the ad first and then you purchased the product. So in this case, B is going to be that catalyst. It's going to be what happened first. This has happened. So normally on your decision trees, right, whatever, if you're doing an experiment or what have you, right, you have one branch to signify, okay, this has occurred, and then you make your next decision, and then this has occurred, right? So if we're looking at this case here, in our case, B is going to be you saw the ad, right? So when we go to do this, this is the probability of B. This branch here is the probability of B, which means not B, right? You either saw the ad or you didn't see the ad, which means down here is the probability. Oops, one more time, the probability. There we go. The probability that you didn't see the ad, right? So that's how it works. So if they're telling us that perhaps in our example, the probability of B, they tell us is 0.125 or 12.5%, then how would you calculate not B? Well, all probabilities add to 100 or 100% or 1. So then we subtract 1 from your B to get 0.875. Right? So that's how it works. We either saw the ad or we didn't see the ad, right? So then in your next decision, right? Decision 1 has been made. You either saw it or you didn't. So then what occurs next, right, is based on, so if we purchase the ad over here, is that B has already resulted. You saw the ad. So you saw the ad and then you either purchased the game or you didn't purchase the game. So this branch right here is signifying that condition. The probability that you purchased the ad, given that you saw the commercial came first or the ad came first, and then you bought the game. Versus the below down here is the condition that you didn't purchase the game, but you already, again, you saw the ad. So that's what your branches are. Every time you make your decision tree, these are what your branches actually mean now in the context of our condition. So if, again, they told us that A is 0.2, again, this is coming from your textbook, then what's the condition that we didn't buy the ad? what's 1 minus 0.2 to make 0.8 or 80% that we did not end up purchasing. So if we do it one more time here, right, we did not see the ad. However, we still bought the game. So even if we didn't see the ad, this has already resulted. However, we ended up getting the game. The probability that we purchased the game, given that we did not see the ad. It had already happened, we just didn't see it. So if we know that the probability of A, given that we didn't see the ad, is 0.1, then the other side of it is what? Probability that we didn't see the ad, given that we did not buy it. 1 minus 0.1 is equal to 0.9. Now, our end results, right? Your end outcome here is that they've now both happened simultaneously, right? Which we now know how to calculate as down below. Here, the probability of B, it happened first, and then what resulted next? The probability of B times the probability of A such that B. 0.125 times 0.2 is 0.25, right? Let's do it again. Over here, we have the probability of 0.125 times 0.8, right? And we can keep going. The probability, 0.8575 times 0.1, and again, one more time, 0.875 times 0.9, okay? So when you are making your decision tree, it actually has so much context to it. And at the end of your decision trees, these are all of your sample spaces. So now let's actually do something that we've done before in example 2. An experiment consists of tossing 2 coins. The first coin is fair, while the second coin is twice as likely to land with a heads facing up as it is with tails facing up. Draw a decision tree to illustrate the probabilities of all outcomes. So I would pause the video, or at least pause it halfway through this problem to see if you can at least get it going. So normally, on a normal coin, right, we have heads and tails, which is half and a half, right? However, on your weighted coin, we still have heads, we still have heads and tails. However, heads is twice as likely to come up. So keep in mind what we did back in our chapter, I want to say that was like 7.3 when it's unlikely or uneven, right? Twice as likely means 2 heads for every 1 tails. So instead of being here as 1 heads out of the 2 outcomes, right? 1 tail out of the 2, we have 2 heads out of the 3 total outcomes, 1, 2, 3, or 1 tail out of the 3 total outcomes. Now this is going to be your unfair coin, because we are tossing 2 coins. One is fair, and the second coin is different, which is twice as likely. So if that's all you needed, please pause the video and try and get started. So if we have coin toss 1, our first coin, we have a heads and a tails. Okay, so we toss your coin, There we go. We toss your coin, we either get a heads or we get a tails, right? And so the probability of your first coin, the fair coin, what would be the probability of H here? The probability of tails. This is your first fair coin. Well, it's either going to be 50-50. So then when you toss your coin again, now this one is going to be the unfair coin. So each of these, that's its own. There we go. We have heads here, tails, heads here, tails. Now we said the unfair coin, right? When we go to flip your unfair coin, it's now 2/3 to 1/3, 2/3 to 1/3. Again, your first coin here, this has already happened, and then we flip your next coin, and as a result, this happens next. So then if this is your end result, this heads and a heads means this is the probability of a heads occurring and another heads occurring, which means it's 1/2 times your 3/2. I'm sorry, 2/3. 2/3, which makes 1/3, or about 33%. Okay, so hopefully this part made sense as to why now this is and this is still the conditional part. Let's try it again. So a heads resulted and then a tails resulted to then make the probability of a heads and a tails 1/2 and 1/3 for 1/6, or about 17%. And again, one more time. Now this will be the exact same, just a different looking outcome. You landed tails first, and then the next result ends up in a heads, tails, and a heads. And one more time, tails and a tails. And there you have it. Again, your sample space, how we've been reading it at the very end, we've been using a lot of this part, is that these are all of your different outcomes. And I'll write that here. Sample space. These are your all outcomes. And there you go. All right, so let's have you guys try your own decision tree. So if you haven't paused the video yet, definitely pause the video here and see if you can make sense of it. All right, so if this is the probability, the probability of A, then the probability of B is just its reverse, so not A. So 1 minus 0.6 is going to give you 0.4. Okay, the probability of 0.2 is going to be up here on this branch. So then this branch, as a result, 1 minus 0.2 is 0.8. And again, got 0.9, so 1 minus 0.9 is 0.1. Now, what do these outcomes look like? Well, A and C is really equal to 0.6 times 0.2, which is 0.12. This branch being the result of A and a B, sorry, A and a D, 0.48, which comes from 0.6 times 0.8. And again, B and C, just doing it again, 0.4 times 0.1. And again here, 0.4 times 0.9 is 0.36. This would be the probability of B and D. So hopefully that makes sense. If you have more branches, maybe you have one in the middle, make sure that they all just total to 1, okay? Now, independence. So independence is the probability of an event A occurring does not depend on whether the second event has occurred B or not, which means they are independent. So if they're independent, that means this condition, right, the probability of A given that B has already happened is actually just equal to the probability of A itself, which means if this used to be the equation of A and B under a certain condition, the probability of B times the probability of A given B. Well, since this here is equal to this here, then we're just going to replace it. If they are independent, the probability of B is now the times the probability of A. So now what we're going to have to do is test for independence. So for an example, assume that the phase of the moon has no effect on whether or not the newspaper gets delivered in the morning. So downtown Charleston aside, very unusual case, we're below sea level. The probability of a full moon M on a random day is about 0.034, and the probability of a newspaper being delivered on that day is 0.2. Find the probability that it is a full moon and the paper is delivered. So we want to know the probability of a full moon and your delivery happening. Well, if they're telling us that they have that they're independent, which we can assume because they've told us here, assume that the phase of the moon has no effect, right? No effect here on whether or not the newspaper gets delivered. So they're telling us it's independent. So when we go to find your condition, or not your condition, your and aspect, we're just going to multiply the probability of the full moon or the moon phase times the probability of delivery. 0.034 times 0.2. This results in 0.0068. All right, now we're going to be testing independence. So to test independence, we compute the probability of A, the probability of B, and then the probability that they happen together. Now, if the probability of A and B, right, when we go to calculate, so once we found all three of those, we then want to test, okay, if A and B is then equal to those two probabilities being multiplied, if they come out to be equal, then the events are independent, right? We said, hey, they're independent, therefore we can multiply them together. Now, if those values are different, so if this value, the multiplication between the two, and then our finding the and aspect, if they're different numbers, then we are able to conclude they are dependent on one another. Now, I want to be very specific. This and right here is find given the event. So this one is from the, what is it called? Let's see, find given the event. Yeah, we have to find it given the event. So I sometimes have a hard time reading what my notes are saying. Now this one is find by the independence of multiplication. So this one you need to calculate. This one we're going to find based on the event. Maybe that's what I say, based on the event. Now, if these are the same, if these are the same number, then independent. Okay, so for example, rolling two distinguishable dice and observe the numbers facing up. So we got two distinguishable, indistinguishable, so red and green, right? Red dice is even, but B is the dice have the same parity. So same parity meaning either they're both even or both odd. So let's figure out, well, what is the probability of A? A being that red is even. Okay, so if they're even, right, what that would look like, let's say we got 2, 1, we got 4, 1. Actually, let me restart. 2, 1, 2, 2, 2, 3, dot, dot, dot. And again, we're only looking at the even ones. So let's say we can skip 1, we can skip 2. Instead, we go 4, 1, 4, 2, 4, 3. And again, keep going. These are 4s. We can skip 5. That's not even. Instead, we go right to 6, and we have the same idea here. 6, 6, and that one. Okay. Right. So if this is what it looks like, that A, the red one, is going to be even, right? How many total different ways can A occur? Well, if it's 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, then this one has 6 different ways. Doing it again for 1, 2, 3, 4, 5, 6, another 6. And then again, another 6. So 6 plus 6 plus 6 is then 18. So then what is the probability of A? A being that one is even, is 18 out of 36. So 1/2. Now do the same thing with B. So if you did not pause the video, I would say pause the video and try out B. B being the same parity, that they're both odd or both even. The probability of B is that they are both odd or both even. So what does that look like? Well, B might look like, right, if they're both odd or both even, right? Let's start with 1 and 1. Those are both odd. 1 and 2, does that work? No. 1 and 3, that works. 1 and 4, does that work? No. And then 1 and 5. Okay. 1 and 6, does that work? No. I'll just write it down just to show you. Okay. Move on to 2. Does 2 and 1 work? No. Right? But you're kind of hoping to get the idea here. 2 and 2 works. 2 and 3 does not work. 2 and 4. 2 and 6. Keep going, right? 3, 1. 3, 3. 3, 5. 4, 2. 4, 4. 4, 6. 5, 1. 5, 3. 5, 5. 6, 2. 6, 4, and 6, 6. So this is all of B, right? So then how many different ways can B occur? Well, one is 1, 2, 3. 2 is 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 18, which means the probability of B is again 18 over 36, or 1/2. So you've calculated A, you calculated B, so now let's figure out the probability of A and B. Let's see that we said red is even and both same parity. So what does that look like? Well, red is even, so we're looking at these ones over here. Red is even. Now we need to make sure that we're doing both even or both odd, right? So if we were to look at some of these, that would look like 2 and 2, 2 and 4, 2 and 6. Let's see, red has to still be even, so 4 and 2, 4 and 4, 4 and 6, 6 and 2, 6 and 4, 6 and 6. So this is A and B, right? Red is even. This can all be the red one here. And then both of the same parity. So because your red is even, then that means we're only looking at your even options. So then what is A and B, or how many? We have 9. So then what is the probability of A and B? 9 out of 36, or I believe that's 1/4. So if this is how you get to this value, right? A and B. Now let's test for independence. I didn't realize how large I was writing. Let's see, can I move some of this up just a little bit? Let's move that up. Let's move all of this up. Now this is a little excessive as far as work goes, but I like showing you all of the things. All right, so test independence. We know that the probability of A and B is equal to the probability of B times the probability of A, which we know the probability of B is 1/2 times the probability of A is 1/2 to be 1/4. Now, are they equal? Is this one equal to this one? Yes, they are equal. So what can we conclude? If they are the same, if they're equal, these are independent. So one does not cause the other. All right, let's do it again with example. Did I add an example in here? Example 5. So roll two distinguishable dice and observe the numbers that face up. A is the sum of the numbers is 6, and B is that both numbers are odd. All right, so pause the video, see what you can come up with. So the probability of A is that the sum of the numbers is 6. Sum to 6. So that looks like 1 and 5, 5 and 1, 2 and 4, 4 and 2, 3 and 3. We're working with indistinguishable dice, so repeats are okay. So the probability of A, well, this is the number of A, is 1, 2, 3, 4, 5. So we have 5 out of 36. All right, so they sum to 6. That's part A. B we said that both are odd. Both odd. Okay, so what does that look like? So B is just 1 and 1, 1 and 3, 1 and 5, 3 and 1, 3 and 3, 3 and 5, 5 and 1, 5 and 3, and 5 and 5. This is B. So how many in B? B is 9 again. So the probability of B is 9 out of 36, or again, 1/4. So now let's look at them both happening. The probability of A and B, which is they sum to 6 and are both odd. Okay, so they sum to 6 and they are both odd. So looking at these ones, right, they have to sum to 6 and they're both odd, which means there's only 3 different ways. So 1 and 5, 5 and 1, 3 and 3. This is A and B. So the probability of A and B is equal to 3. So, oh, sorry, 3 out of 36. Now let's test for independence. We have the probability of A and B is equal to the probability of A times the probability of B, where we said this is 5 out of 6. Oh, sorry, 5 out of 36 times 1/4, which is 5 out of 144. Now, does that equal this? No, they are not equal, therefore they are dependent. Which means in order for them to sum to 6, right, they both have to be odd numbers. All right, we're going to skip example 6. That I just think that's enough practice. I am taking that off of our guided notes pretty soon. So hopefully that gives you a good head start.